All right, first, anybody have any questions about the vector view? I am going to talk a little bit about, describe some of this stuff, but I'd be happy to go into any questions. I fixed the angle on that one example. Yeah. Anything right now? Okay. Well, let me talk a little bit about vectors. I think even people who've done a lot with vectors in other classes, the way that we're going to use it in this class is maybe in some ways different than how you have before. So I want to just bring up the important points, the things that are going to come up all the time. So let's say this is our example vector. It has a length of 1.5 and it makes an angle of 30 degrees with the horizontal. And in order to do math with this, we want to represent this as components. But before, so that vector, I mean, it's a mathematical object, but you can think of it as like actually a physical thing. It's an arrow in space. Before you can put it into components, you need, so before you can express this as components, you need to define a coordinate system. And what you choose as a coordinate system is going to determine, it's going to affect what those components are. So capital CS, that's always going to be coordinate system in this class. So for example, if you have this vector, and the coordinate system you use is this, where that's the x-axis and that's the y-axis, then that vector v is just 1.5 in the x direction, positive x direction. So 1.5 I, 0j, you can just leave that off. And the notation that I'm going to use is the x component is on the top, so 1.5. The y component's on the bottom, and then it's in square brackets. That notation is nice for doing matrix calculations. There are a lot of things, a lot of reasons that you multiply vectors by matrices, and this is the format that you need to in order to do matrix math with these. On the other hand, if you start with that same vector, with that length 1.5, and the coordinate system you use is this, and the vector components are going to be 1.5, the length of the vector, times the cosine, let me write that as 30. So cosine of 30 degrees, sine of 30 degrees. So if you multiply all that out, you get 1.299, 0.75. Okay, so same vector, but the components are different depending on what coordinate system you choose. In 3D, we're going to do a lot of stuff with 3D vectors also. So if you think of, the x component in the x direction plus the y component in the y direction plus the z component in the z direction, the notation is going to be x, y, z as a column matrix like that. Once you express the vector in components, it's easy to do math with it. So here are the calculations that we're going to use over and over again. This one is multiplying a vector by a scalar. A scalar is a number that can be positive or negative. So if you have a vector A, B, C, and you're multiplying it by the number D, that's the scalar. The components that you get out from this are dA for the x component, dB for the y component, and dC for the z component. Physically, what does it do to a vector when you, so if you go back to thinking of the vector as an arrow, what does it do if you multiply that vector by 2? Yeah, it makes it twice as long. What does it do if you multiply it by -2? Yeah, changes the length by that, by the magnitude of that, the absolute value of the number, and then flips the direction. But this is how it works mathematically. You can add two vectors. So if you're adding the vector A, B, C to the vector D, E, F, you get an x component that's A plus D, a y component that's B plus E, and a z component that's C plus F. In your, well, in TI calculators, does anyone have a calculator that's not Texas Instruments? Yeah. What kind do you have? HP. Okay. So if you want to talk about this later, we can talk about it. But okay, if you're used to that, that's good. In TI calculators, the notation is like this. Well, there are only two ways, and the Inspire I think is different, but this is for TI 83, 84, 86, and 89. And there are two kinds of notations. Some calculators, some of these models accept either of these two ways. Some only accept one. You just have to try them both out. But here are the two ways. So like, for example, to do that addition, you would enter the matrix. So this is the first way. A square bracket for the entire vector, and then square brackets for each row in the matrix. So, with a column vector, the rows are just a single number. If you're doing a matrix, you have commas between the values in the row. So I'll write this as A, B, C. Just use the regular plus. D, E, F, and if you enter that in, it'll spit out the right value, you know, A plus B, B plus E, C plus F. And same thing with multiplication. You just use the regular multiplication. You know, D times, you represent the vector this way, and it'll do that calculation for you. 89s, TI-89s, if you enter variables in, it'll do the calculation with the variables, which is nice. Maybe some of those other three do, but I know they don't all do it. But there are ways around most of this stuff. And so if you can't figure out how to do something on your calculator, come talk to me and I'd be happy to work it out with you. The other way saves some keystrokes. I know it works on the 89. It might be the only one, I'm not sure. Is instead of a square bracket for each row, you use a semicolon to separate the rows. So this would be A semicolon B semicolon C, close square bracket, plus D semicolon E semicolon F, close bracket, and you get the same thing out. Then another thing that we're often going to want to do is calculate the length of vectors. So if your vector is A, B, C, then the length of that vector, we'll write it like an absolute value. That's the notation for the magnitude of a vector. It's just the Pythagorean theorem. It's the square root of the sum of A squared plus B squared plus C squared. On a TI-89, I know there's a function norm. So if you enter norm, and then in parentheses you enter this vector, so I'll do it like this, A, B, C, it'll give you that value. So it'll do that for you, which is nice. If your calculator doesn't have it, it takes 2 minutes to enter a program that'll do this, and then you still never have to type it in. So again, with all this stuff, come talk to me. I don't want you to have to worry about, you know, like punching in right formulas or whatever. That's not a good way to spend your time, you know. Let's get your calculator set up to do it automatically, and then you can just think about the concepts instead of worrying about the details. What? Yes, that's right. It's a scalar. And then there are 2 ways to multiply 2 vectors together. Anyone know the names of these 2 ways? Dot product, yep. And when you take a, that's right, cross product. When you take a dot product, so you're multiplying 2 vectors together, what do you get out, a scalar or a vector? Scalar output, yep. So the output is a scalar. Sometimes you hear people refer to this as the scalar product. And the second way is the cross product. And what type of mathematical thing is the output of a cross product? Vector. And so sometimes you hear people talk about cross product as the vector product. Okay, so let me do these one by one. So first, the dot product. If you take the dot product between a vector ABC and a vector DEF, the output is A times D plus B times E plus C times F. On a TI-89 again, there's a built-in function for the dot product. The function is called little dot and then capital P, dot P. And so you'd, in the catalog, look up dot P. As the argument, put in your two vectors separated by a comma. And it'll give you the answer. And just like with all the other stuff, if your calculator doesn't have that built in, let's put it on there. And then you never have to enter this stuff. There are a few things about dot products that are important to remember. So notice, first, I guess I already mentioned this. It's often called the scalar product. Because the output's a scalar. Second, the dot product of two perpendicular vectors is 0. And third, the order of operation doesn't matter. Order doesn't matter. And so what I mean there is a vector A dotted with a vector B is the same thing as B dotted with A. Okay, the second type of matrix multiplication is the cross product. You can write it as a formula I think probably most of you, when you learn cross product, the people who've done it before use that determinant idea as a sort of memory device. The memory device, as always, that I recommend is having it in your calculator and not having to remember it at all. It's flash memory device. But here's the formula: ABC crossed with DEF is equal to BF minus CE, and then AF minus CD, and this one's negative, and then AE minus BD. And so for each one of these components, you get it by crossing out whichever component, like on both of these two vectors, cross out the component we're looking at. So if we want to figure out the x component, cross out the two x values, and then multiply across there, minus multiplied across there. And what's the deal with the negative on the y? The y component just always has to be difficult. That's just going to come up over and over again. Like the y component is like, it's kind of playing the same, playing along or whatever, but it just thinks it's a little special, you know? Like did you, like in high school, did you ever know anyone who like took a like summer trip with their family to Scotland and then came back and had like a Scottish accent for like the last 2 years of high school? No, that's the y component. It's just like, yeah, it thinks it's a little better than x and z. It's always got to be a little different, you know. So look for that. Right? Yeah, look for both. Yeah, anybody with a Scottish accent, they're making it up. That's not a real accent. And on a TI calculator, there's also a function for that. Well, on TI 89s anyways. And I'm sure Inspires have all these too. I'm not totally sure about the syntax. I'll figure that out. On a TI 89, the function is lowercase cross p. And so if you go cross p of A, B, C, and D, E, F, it'll give you the answer. You never have to think about it again. Okay, so what are the requirements for a coordinate system? Well, I should say the requirements for a right-handed coordinate system. Any coordinate system you've ever used is right-handed. There apparently are some applications where you use a left-handed coordinate system, but I've never done anything where you had to use anything but like a normal right-handed coordinate system. And the requirements for a right-handed coordinate system, an acceptable coordinate system, come from the cross product. And the requirements are that if you take the cross product between the x-axis and the y-axis, you get the z-axis. Take the cross product of the I-axis the x-axis and the z-axis, you get the negative j-axis. Okay, that again. Got to deal with this again. And then the third one, j crossed with k gives you I. Yes, thank you. This should be k. Thank you. That would be a really tough requirement to meet. Yes. Yeah, it'll be online. And actually, something very much like this is already there, from when I did this lecture last year. So like if you ever want to read ahead or something, you can look at the notes under old lecture notes, and it'll be pretty similar to what I'm going to talk about. And then, any questions about that? So if you use a coordinate system that doesn't meet these three requirements, then things are going to go haywire in your calculations. It's not an acceptable coordinate system. A few things to notice about cross product. First, the y-axis always has to be the weird one. So don't forget to make the y-axis negative if you're doing the cross product by hand or using that formula. Second, the cross product is often called the vector product. Because the output is a vector. With the dot product, remember, if you took the dot product between two perpendicular vectors, you got 0. With the cross product, if you take cross product between two parallel vectors, you get a 0 vector out. And that's true whether they're in the same direction or opposite directions. By the way, another thing that name you hear for dot product is inner product, and another one that you hear for cross product is outer product. And those make sense if you think about inner as being like, in is meaning sort of parallel to each other in the same direction, and out as being out of parallel. Then a dot product in some sense is a measure of how close things are to parallel. How it's a measure of how in parallel they are. And the cross product is a measure of how out of parallel they are. So that's called the outer product. And then the last thing to remember is that for dot product, remember, the order doesn't matter. A dot B is equal to B dot A. That's not true with cross product. So the order does matter for cross product. A cross B is equal to negative B cross A. That can be I mean, it's not a complicated concept, but it can slip your mind very easily because we're not very used to multiplication order mattering, you know. So you have to be careful with this one. Our cross product formulas, and we're going to have a few of them, list things in a certain order, and if you switch that order, you switch the answer. Any questions about any of this so far? Okay, the next thing, this is going to be really important in this class, is calculating a vector that goes from one point to another. So let's say we're going from the point A to the point B. There are two ways to do this. Sometimes one's easier, sometimes the other is easier. First, if you already have the coordinates of the 2 points, then you can just subtract the coordinates. If the coordinates of point A are given by the vector A, coordinates are just vectors pointing from the origin to the point that you're looking at. So you can think of these coordinates as a vector. And if the coordinates of B are the vector B, then B minus A is the vector to B from A. So you always take the coordinates of that destination point and subtract the starting point. The other way you can think about this, that's going to be more useful in this class because usually you're not going to be given coordinates of these points, is to think of the starting point as the origin and just calculate the coordinates of the destination point. Okay, so let me do a couple examples. So first, what's a vector that goes from uh, 10 to the point -4, 6. We're already given the coordinates of those points, so we're just going to take the destination point minus the starting point. So negative 4, 6, minus 10, 2, and you get negative 14, 4. And so to visualize that, we want to go from 10, 2, which is, let's say, here, to the point negative 4, positive 6, which is here. So the vector from that starting point to that ending point is this. And if you think about what the components of this vector, think about putting the tail of this vector at the origin. What quadrant would that be in? We know that it makes sense to have a big negative x value and a smaller positive y value. And that matches the answer that we got. Okay, this is the technique that is going to come up more often. So let's say, make it sort of a physical problem. Let's say we have a cantilever beam connected to the wall over here. This is the point B. This is the point A. Say that this angle is 30 degrees. That's supposed to be horizontal. And the length of this is 0.5 meter. What's the vector to the point B from the point A? And then let's do that, and then let's also do the opposite. What's the vector to the point A from B? So for the first one, we want this vector. We know this angle is 30 degrees. So we're going to put the origin of the coordinate system at the starting point. And now we just have to calculate the coordinates of this other point. So if this length is 0.5, that vector is 0.5 times, if you have a way of doing this that you're happy with, keep doing it. But you can always just figure out the counterclockwise angle from the x-axis, and then you don't have to worry about the signs, the quadrant, anything like that. So I'm just going to say it's 180 degrees to get there. We're trying to get to the red, so we didn't quite make it to 180. We were 30 degrees short of that. So cosine and sine of 150 degrees. So 0.5 times cosine of 150 sine of 150. And that is negative 0.433, positive 0.25. Any questions about that? For B, now we're trying to figure out the exact opposite vector. So the easy answer to this is all we're doing is switching the signs of the components. So the answer needs to be positive 0.433, negative 0.25. But to think about it this way, we put the origin at the new starting point. This angle is 30 degrees. Well, this angle is 30 degrees because this one is. So that's like one of those questions you had to do on the SAT. This is 30, what's that angle? There's some name for that you learned in geometry. Vertical angles? What is it? Alternate angles? That sounds, yeah, I bet you're right. Okay, so in this case now, it's either 360 minus 30, so 330, or you could just go negative 30, and you get 0.5 times cosine of negative 30 sine of negative 30. And you get positive 0.433, negative 0.25. Any questions about that? The next thing that we're going to have to do all the time is calculate unit vectors in a known direction. In a given direction. And there are two ways to do this. First one is given an angle between some reference and the desired vector. This is only useful in 2D. 3D, you don't want to mess around with this. You'll just spend a lot of time you don't need to. It can get really complicated. The other one is in the direction from one point to another. And this one is useful in 2D and 3D. Okay, so if the information you're given is angle information, let's see here. So let's say you know that this incline makes a 20-degree angle with the horizontal. And then the vector that we want makes a 40-degree angle with the incline. We want to know what the unit vector, well, what's the unit vector shown? What's the unit vector? What are the components representing that unit vector? Okay, so the way I like to think about this, so in order to use cosine and sine for a unit vector, you need an angle that goes counterclockwise from the positive x-axis. I'm just going to, and okay, you need an angle that goes counterclockwise from the positive x-axis when that vector's tail is at the origin. So I'm going to just set up a bunch of vectors, figure out the, let's see. So what do we know here? I can draw a vector like this, where this angle is 20 degrees. That vector is parallel to that incline. And then I know that the vector we want makes a 40-degree angle with the negative of that vector that I just drew. Okay, so this is the one we want. So how do we figure out the angle from the positive x-axis counterclockwise to the one that we want? Is everyone with me here? I stumbled over my words on that one. You follow what we're trying to do? Or like why I drew this picture I drew? I just drew all the stuff up here so that I could use the references that were given. And now what I'm going to do is just piggyback from one thing to the other, going counterclockwise, positive, and clockwise, negative, to figure out the angle here. So start at the positive x-axis, counterclockwise 20, right? So now we're at plus 20. Add another 180 to get there. So now we're at plus 200. Now subtract 40, because I'm going clockwise from here. So we have 200 minus 40, and so the angle from the positive x to this is positive 160. So theta is equal to, I'm going to write it as plus 20 plus 180 minus 40. That gives 160. And so the unit vector, I'll write it as u with the pointy hat, is equal to cosine of 160 sine of 160. Yes? Where to place the 20 and the 40 when I was adding those things up? Oh, yeah, okay. Yes. I just kept doing these from references that were given. Like, we know that it's 20 degrees from horizontal to get to a vector pointing like that because it's given. You know? And then that's a vector pointing that way. we know it's 40 degrees from a vector pointing the opposite way to this. Okay, so I went 20 degrees to get a vector pointing there, then 180 to get the opposite vector, and then backtracked 40 to get to this vector. It's always 180 between a vector and its opposite. That's right. And that is negative 0.940, positive 0.342. So the nice thing about that thing, just figuring out what the angle is counterclockwise from the positive x-axis, is it's always cosine for x, always sine for y. You never have to deal with the sign, the plus minus signs. It does all that for you. You know, I think that's a nice way to do it.
Unit vector only gives direction.
Yeah, you can think of any vector as, you can break up any vector into magnitude multiplied by a unit vector, and you can think of the unit vector as being the pure direction, and the magnitude is the length. Yep. So let me do an example like it would come up in statics. So let's say that we have a bar with a slot, and another bar is connected to the first one by a pin that can slide in that slot. So the pin here is attached to the horizontal bar, and it can slide up and down that slot. It can also rotate, because that pin can just rotate freely. So if I take let me both names, I'll call this member, the horizontal one, member 1, and the vertical one, member 2. Since this can slide freely in that slot, the connection between bodies 1 and 2 doesn't apply any force to one parallel to that slot, right? It's free to slide up and down. All that this slot does is prevent that pin from moving perpendicular to the slot. Okay. So, let me give this angle too. Let's say this is 50 degrees. If I draw a free body diagram of member 1, we know that the force applied to member 1 by member 2 is perpendicular to this. So we'll say there's some unknown force. We don't know the magnitude of that force, but we know the direction is perpendicular to that dotted line. And I'll say the magnitude is R. Okay, we're going to, in statics, we'd calculate that later. And we know that the angle here is 50 degrees. What we want to do is calculate a unit vector in the direction of that vector that's drawn. And then if we multiply that unit vector times this magnitude r, what we have left is a vector in our known direction with a magnitude equal to r. And if we solve r, we know the magnitude of the force. So I'm going to do this the same way I did before. So here's the coordinate system. That first vector a vector that's parallel to the dotted line is counterclockwise 50 degrees from the x-axis. And then that vector that's labeled r is 90 degrees from the first one. And so to come up with a unit vector for this one, what's the angle? Well, from the positive x-axis, we go positive 50, and then we go another positive 90. So 50 plus 90 is 140. So theta is equal to plus 50 plus 90, 140. And so the unit vector is cosine of 140, sine of 140, which is negative 0.766, positive 0.643. Now the last step is if we're trying to figure out the force vector, so then the force vector F is equal to the magnitude R times that unit vector. And now what we have there, this is a really useful thing that, you know, I don't expect this to like 100% make sense yet, but we're going to do a lot of this. What we have is, even though we don't know either one of the components for this force vector F, we've expressed this force vector F in terms of a single variable. So if we didn't know anything about that force vector, we'd have to solve for two variables, an x component and a y component. And for that, you need two equations. What we have now is expressions for the x and y component that only depend on one variable. You only need one equation to solve for it. So that's going to be sort of a key idea. Any questions about that? Yes. Well, I said, and we're going to go into a lot of detail on this, but the key fact is that the force applied to member 1 by member 2 has to be perpendicular to that slot. It can't be parallel to that slot because it slides freely. So if it's sliding freely, there's no force applied. The only thing, there's a force applied that prevents it from moving perpendicular to the slot. And so this R is a vector that's perpendicular to the dotted line representing the slot. I could have just as easily drawn it the other direction, and it would work the same way, even though the signs would be switched. In the end, if I draw it this way, I'd get, say, a positive value for R. If I had arbitrarily chosen the other way, when I solved it later, I would get a negative value for R, and it works out just the same. Any other questions? Okay, so this was all along. So remember, here's where we are. I'm talking about calculating unit vectors. I said there's two ways to calculate unit vectors. If you're given an angle with a reference, and that's what we've been talking about. And the other way is if you want it in the direction from one point to another. So that second one is a unit vector that's in the direction from one point to another. And the steps for this are calculate a vector from, let's say, one unit vector in the direction from one point, I'll call that A, to another, I'll call that B. The first thing we're going to do is calculate a vector from A to B. And then the second step is find the unit vector in that direction. We've already talked about how to find a vector, calculate a vector from one point to another one. So we're already done with this. To find a unit vector in that direction, let's say that our original vector is u. Okay. The magnitude of that vector, you know how to find that. That's the sum of the squares, all square root. And then the unit vector, the thing we want, u pointy hat, is equal to 1 over u. Okay, 1 over the magnitude that we just calculated times the vector. Okay, so let me do an example here. So let's say that there's a bar that's connected to the wall by a pin joint. So let's say it's free to rotate around this pin joint. So there needs to be another force holding it up to keep it from swinging down. And the thing that keeps it from swinging down is a cable that's attached from here over to the wall. So here's a cable. Let's say the coordinates of this point are 2.51. And the coordinates at this point are 4.52. If the cable tension is T, what's the force vector applied to the bar by the cable? Well, the overall idea is the same as it was in the last example. I want to find a unit vector that points from the bar, that points in the direction from the bar to the wall. And then I'm going to multiply that by the scalar t, and that'll give us a vector that has a magnitude of t and is in the desired direction from the bar to the wall. Yep. Yeah, a cable is always applying a force away from what it's attached to. That's right. And again, that's another one of the things where we're going to go into a lot of detail. Right now, I'm trying to give mathematical examples, but we haven't talked about the physics much yet, But so first, let's just figure out the vector that goes from here to there. So the vector we want is going in this direction. So the vector from here to there, I'll call that u, and it's equal to 4.52 minus 2.51. And so that vector is 2, 1. And now we have to calculate the unit vector. So the magnitude first is equal to 2 squared plus 1 squared square root. So that's root 5. And so the unit vector is 1 over root 5 times the vector 2, 1. And I think that comes out to be 0.894. Do I have that here? I don't have that. Is that 0.894, 0.447? Okay. So that's the unit vector. And then the force vector is just t times that unit vector. So 0.894 t, 0.447 t. And one more thing on a TI-89 calculator. There's a function called unit v, where you input any vector, and it'll give you a unit vector in that direction. So if you go unit capital V, you don't have to remember these formulas. You can look them up in the catalog and just scroll down to the function. So unit V, enter in, I guess the vector that we would want is 2, 1. And it'll give you back 0.894, 0.447. And again, like if you don't have a TI-89 or an Inspire that does this automatically, it's easy to put a program in that'll do it, so you don't have to think about the steps. Save, brain space for the stuff we want to instead of worrying about these calculations. Any questions about that? All right, well, let's stop there, and then next time we'll get into statics of particles. We'll finally get some statics. Yeah, so that's it. Have a good weekend. Yep. Yes.